So our next topic is policy iteration. Policy iteration begins by initializing the policy randomly. And then you see there's a repeat until no change in pi. So there's a loop, outermost loop, where you keep repeating something until there's no change in pi. In other words, each time you iterate through this loop, you are changing the policy pi. And so until there's no change in the policy, when it stabilizes, then you quit this algorithm, and this would have converged to pi star s. Pi star for all states s. Now, what's inside this outermost loop is two steps. So this is the first step that I've shown here. And this first step is another repeat until converged. And so what we are doing is we are simply applying Bellman's equation under this policy pi, which was initialized randomly for the first time. And then we will be updating pi, remember, not shown here. So this is simply Bellman's equation. And this can be recognized to be policy evaluation. So what we are doing in the first step is we have a policy pi which was initialized randomly, but it keeps changing every iteration, of course. And then for that policy pi, we do policy evaluation. This is the second step. This step is as follows. So the first step converges to V pi of S, where pi is the policy. So once we have completed policy evaluation, then this step, what we are doing is we are extracting the best action for each state S. So we iterate through each state S, and then using the values that we obtained, which is V pi S, we now improve pi. So we are updating pi to be equal to the best possible action. Now this is not exactly the best possible action because this is not the optimal policy yet. Let's remember that. But it still is policy improvement. So what we are doing is we are, once again, the first step, we found out for our current policy pi, we found out the values of all the states. And now in this second step, what we are doing is we are now updating the policies. And this is the complete algorithm. And eventually we will assume it to be true. I will not prove it, but it will converge to pi star S. Now let's look at the algorithmic complexity of policy iteration. Now the first step is repeat until converged of this we already saw to be policy evaluation, and we have seen earlier that the complexity of policy evaluation per iteration is order S squared, where this S is the number of states. We have already seen this. And now I'll tell you that based on convergence proofs, this is linear in S. The outermost repeat loop of policy evaluation is linear in S. And therefore, the first step, algorithmic complexity, is S squared times S, which is S cubed. So this is order S cubed. I have kept spaces here for the next step. So the first step is order S cubed, which is one iteration of the outermost repeat this loop, and it's of order S cube. It is policy evaluation. Another way to look at this is policy evaluation is nothing but application of this vector matrix equation, and that's solved in order n cubed, where n is the number of states, or S cubed rather here, and therefore the algorithmic complexity of the first step is order S cubed per iteration. The next step involves a for loop, which is one per each state, and so that's S number of times, the cardinality of the number of states times, and we have to carry out an argmax over all possible actions. So this is the cardinality of the number of actions, and then we have a summation which is carried out over all possible states. So this is again of order S. Therefore, the algorithmic complexity of the next step is S square A, order S cubed plus S square A. Let's compare value iteration and policy iteration. Now, the complexity of value iteration when doing policy improvement is order S square A per iteration. Now here we saw that the complexity per iteration is order S cubed plus S square A. So obviously per iteration, value iteration is better than policy iteration. So why at all do we use policy iteration? Now, studies have shown that the convergence is linear for the outermost repeat loop in value iteration. Repeat until convergence. As opposed to that, policy iteration, the convergence is somewhere between linear and quadratic. So what happens is you have to repeat the outermost loop less number of times in policy iteration. So that is a trade-off. Although the other for loops outside the outermost loop has a higher complexity in policy iteration, it so happens that the outermost loop will be executed less number of times in comparison to value iteration. So that's a trade-off. You have more iterations of the inner loops in policy iteration, but the outermost loop terminates earlier. And another observation is one doesn't have to keep repeating policy iteration until the optimal values V star S are obtained. As soon as the optimal policy is obtained, the algorithm can quit without running any further. Here's a little example to demonstrate policy iteration. It's going to be another example, not the one that we have dealt with so far. So here we have a grid of 9 cells, and we have an initial cell which is colored green. That's from where we begin. The agent begins rather, that's the initial state, and that's the goal state, the one in blue. That's where the agent eventually will land up in. And we associate rewards 100 and negative 100. So these are the rewards. Once you are in the goal state, or rather the agent is in the goal state, it receives a reward, an immediate reward of 100. And this is some kind of a forbidden state. And once the agent lands up in the forbidden state, it receives a reward of negative 100. Now we have two possible actions, right and up, R and U. Now when taking action R, it's a little randomized, so there's a probability of 0.9 of actually moving right and a probability of 0.1 of moving up instead of right. Also, if the agent is in the right cell, any of the three rightmost cells, then executing action R will land up in exactly the same cell because it cannot move right of the right cell. Likewise, an up move will take you up, will take the agent up with a probability of 0.9, and if it is a top cell, then there will be no change in the state, and with a probability of 0.1, it will be a right move instead. So 0.9 is the probability of taking the correct move, and 0.1 is the probability of taking the other move. There are two actions here, right and up. And we'll assume for simplicity that the discount is 0.5 gamma. So we begin our policy iteration by initializing our actions to random values per state, and so the policy is random initially, and since we have two possible actions, we have two sets of arrows, an up arrow and a right arrow for actions moving upwards and rightwards. Now we will, for this random policy, we will do policy evaluation. So we have to find the values of all these states using the given policy. Now this is the goal state. The blue square is the goal state, and we don't need to evaluate rather we don't need to find an action for the goal state because we are already in the goal state, and so we will assume that it's initialized to some very high initial value V of S, and we'll show the math from the next state onwards. So again, since the goal state does not need any action because the agent has already reached the goal state, so we can assume that the value of the goal state is something very high. It should be around 100. And then we shall, just for simplicity of the arithmetic that follows, the value of this goal state is such that this and this evaluate to 10 each. Approximately, if this were 100, remember that this, what I've shown in the top right here is the actions corresponding to the policy that we are evaluating, and this takes us upwards, so it's only 10% of the time you will reach the goal state from here, so it's approximately 100 here, which makes this 10, and likewise this actually from this cell we are moving right, so it's only 10% of the time you move upwards with this policy. And if this is approximately 100, I'm ignoring the discount. It should be actually around 200 because we have a discount of 100, discount of half. So this is 10, and then I shall show you the real calculations. So now the values are percolating to the other states. So top left, it's 4.74. The policy mandates that the action be a right move. In other words, with a probability of 0.9, we go to the next state which has a value of 10. And it's multiplied with gamma, the discount. And with a probability of 0.1, we go upwards. Now, since this is one of the uppermost cells, going upwards will land up in exactly the same state. So if this value were equal to x, then with a probability of 0.1, we land up in the same state which has the value x. So we solve this equation. X, the value of this state is 0.9 plus 0.9 times gamma times 10 plus 0.1 times gamma times x. And noting that the value of gamma is half, we obtain 4.74 for this state. So the value of this state is 4.74. Likewise, the value of this state is 4.74. And the value of this state turns out to be 5, because either up or right you land up with a probability of 0.1 and 0.9, or 0.9 and 0.1, you land up with a state with a value of 10. And 10 times the discount is 5. So next step of policy evaluation, we evaluate the values of these two states here, and I have shown example calculations for this state here. Let's see what happens. So assume the value of this state is x. Then looking at the policy with a probability of 0.9, it moves up, which has a value of 5. This state has a value of 5, and so it's 0.9 times gamma times 5. And with a probability of 0.1, it moves to this state here, which has a value of 4.74, and so 0.1 times this is the term gamma times 4.74, but we also have a reward of negative 100 for getting into this state, so that also has to be taken into account. And so this gives rise to a value of negative 7.51 for x. We don't really need to evaluate the value of the initial state. Why? Because there's no other action that's getting us into this state, so it's not going to be used anywhere. So now let's begin our policy improvement. So we don't have a value of this, we don't have a value of the goal state either, but we have values of all the other states. And so we do our policy improvement. What do we do in policy improvement? We change our policy. Each state, the action is now going to take us to the one which has the highest possible value. So from here, the initial state, we can either go right or up, but up has a higher value, and so the optimal action here will be to move up. Likewise, from 2.38, we can either move up or we can move right, but if we move right, then we have a higher value of the next state, which is 5 as opposed to 4.74, and so on. And so this gives us the optimal actions for each state, and that's the optimal policy. So this is the final, the next iteration of the outermost loop rather. So this is our new policy. And now we have to evaluate the values of the new policy and keep on repeating until there is no change in the policy. Now this policy makes quite a bit of sense here, because from here the initial state the preferred direction is upward, so that we are avoiding this forbidden state here. And from here we are actually going this way. Why? Because if we go up, then with a probability of 0.1 we could hit the bump here, so which will take us back to the next state. So it makes sense to move this way, and from here you can move up or right. So this concludes our example. The end.